Hey everyone, this is Mr. Mott. What I want to do is talk about and try to explain intramolecular bonding using something you might be familiar with, electron orbitals. So the first thing I have is hydrogen. Hydrogen is an atom that has one electron in it, okay? And so if hydrogen, for instance, wanted to make another chemical bond with another hydrogen, which also has another chemical bond, they'd be happy to pair up, and so here's what we would find, that these two would form a chemical bond, okay? Electrons like to be paired up, and so they would form a chemical bond. Now, so the question is, how are they sharing their electrons, okay? And that sharing depends on electronegativity, okay? What you want to do is look at an electronegativity table and find hydrogen, okay? So here I see hydrogen has electronegativity of 2.1, okay? And so it's an electronegativity table that we use. And so this electronegativity describes how strong each of these atoms pull on the electrons. So what you would do with these numbers is that you would subtract them, 2.1 minus 2.1. And of course we get 0. Now what 0 means is that these electrons are going to be shared equally between them, and we call that an equal covalent bond. Equal covalent bond. Now the equal means they're being equally shared. Co means with, and the valent has to do with what we call these electrons. The outermost electrons in an electron orbital are called the valence electrons. So that's kind of the derivation of how we come up with this weird term, okay? So by looking at the electronegativities and looking at their difference, so we call this the END, the electronegativity difference. That's how we determine what type of bond we have, okay? Next, we're going to take a look at what happens between hydrogen and another common molecule, which is oxygen, okay? So we'll take a look at that one now. So in our picture, we have hydrogen again. In this case, we have two hydrogens. And here is the electron orbital for oxygen. Now, in this particular one, we're only showing the valence electrons. So in essence, it actually would have, it's just sort of informational, it would have another shell here and here. Oxygen has a total of 8 electrons, but only 6, 1, 2, 3, 4, 5, 6 on the outside, or 6 valence electrons. So one thing that we'll touch on a little bit later on is that 6 is sort of not the magic number that we want to get to for most electron orbitals. We want to get to 8. So the fact that hydrogen can donate electrons here and pair up here, and also pair up here, that's going to be the best fit, and it's going to sort of encourage this bond to form. Okay, and so what ends up happening is that these electrons, once they shift over and the chemical reaction takes place, here we have our chemical bond, and here's our chemical bond. So the chemical bond is made of the sharing of these electrons. However, the electrons are not shared equally. From the picture, it sort of looks like they are, but they're not. The reason being is that oxygen and hydrogen have a different electronegativity. Okay, so what I'm going to do, and so looking at a table of electronegativity, you see oxygen has an electronegativity of 3.5, and hydrogen has an electronegativity of 2.1. So we always subtract the big minus small. We get 1.4, and that's going to tell us that we have an unequal covalent bond. So what that means, and what that really tells us, is that oxygen and hydrogen are not sharing the electrons equally. Sort of like if when you're growing up and you're learning to drive, you probably don't have a car of your own. Maybe you share it from with your parents. So maybe they drive it 5 or 6 days a week, and then you borrow it maybe for a few hours on the weekend. That's unequal sharing. Okay. So what does that mean? It means that these electrons are being shared unequally. Since oxygen has the greater electronegativity, it's going to have these electrons more of the time. And so what we do for oxygen is that we draw this partial symbol and we give it a negative. So oxygen has a partial negative charge to it. And hydrogen, since it has these electrons less of the time, we give it a partial positive character. Okay? This bond between oxygen and hydrogen is the same as the other one, so we'll draw a partial positive charge here. By looking at the way that the nature of these bonds helps us understand why water is a polar molecule. Polar means that one side does not look like the other, and so we look at the top side of this molecule. The top side of the molecule is partially negative, the bottom side is partially positive, so that makes it a polar molecule. So the reason for looking at these intramolecular bonds and trying to understand how electrons are being shared helps us understand why a molecule acts the way that it does based on its polarity. Okay? The last thing we're going to look at is how do we make an ionic bond? Okay? Ionic bonds tend to form from metals and nonmetals. Okay? So here's an example, and I'll show the electron shells for sodium and for chlorine. Okay? And so here we see the electron shells, and again, the only ones that we're going to be interested in that are involved in bonding are the outside electrons, okay, our valence electrons. So we can see that sodium has one valence electron in the outer shell, and chlorine has 7. 1, 2, 3, 4, 5, 6, 7. Now, chlorine would really prefer to have a full outer shell, which means 8 electrons. And so would sodium, except for it's going to be really hard for sodium to gain an electron or gain 7 electrons. So the easiest thing for that it can do is that sodium will donate its electron to chlorine. Now, the reason being is based upon the electronegativity. Okay, and so what I'll do is kind of show our picture now of what the atoms look like once they've been donated. Kind of see a before and after picture. Okay. So what we see is that this is our before picture and this is our after picture. So this right here is the electron that was donated. And what you're going to notice now is that Na has a plus symbol written in here, Na plus, compared, and Cl has a Cl minus. Okay, so let's just focus on this picture now and try to understand exactly why this is a full positive and this is a full negative. So in this case, what happened is that chlorine took the electron completely away from sodium. So this electron now lives with chlorine, and because now it has one extra negative part, it takes on, chlorine becomes a full negative charge. And sodium lost a negative, so that's why it becomes positive. Looking at the electronegativity, chlorine has the larger electronegativity at about 3.0, and sodium has electronegativity about 0.9. So when you subtract them, we get 2.1, and this, according to our electronegativity chart, is an ionic bond. And in an ionic bond, what ends up happening is that electrons are transferred. Okay, so the electrons are transferred, and what you want to think about is that the larger electronegativity has that greater pull on the electrons. So sodium, that's why chlorine takes the electron from sodium, and now it lives there permanently. So that's why sodium has a full positive charge. It totally lost the negative. It doesn't have it at all anymore. And chlorine has the extra negative, the extra electron, and now it becomes negative. Okay. Another little aside with this, ionic bonds always form between a metal and a nonmetal. In this case, sodium is your metal and chlorine is your nonmetal. Okay. Hopefully this has helped understand a little bit about intramolecular bonds, and It's an important topic to understand because it helps us understand the molecules as a whole. Thanks for watching.